Okay, so we're live now? Hey, what's up? Hello. Hello. I'm just going to enable the camera real quick. Um, Let me just set this up real quick. So if I change my hello everyone. Okay, so this should be okay. Here we go. Okay, right. Does the camera look fine to you? Is it like reflected or something? It's fine. Yeah, the stream works too. I have both the camera and the stream going right now. Yeah, you can look at both. Yeah, because I'm just streaming it to get it on YouTube as well. Okay. Anyway, so welcome back. So this is the fifth session. So we're gonna do the first half of chapter 5. Um, so what we're gonna do here? We're learning about eigenvalues and eigenvectors, and what's so important about these guys. So basically, the whole idea of this chapter here is we're basically looking at maps from from vector space V to itself, right? And the whole idea here of so these maps are extremely important in linear algebra, right? So these guys are called operators, right? And what are so these maps that map for vector space itself, these maps that are linear maps are called operators. And these linear maps, it turns out to have very important properties. So one of the properties which we will be proving today is that if you have a linear map from some vectors, so let V be a vector space over C, where a dimension of V is at least 1. And it turns out that these maps here, right, always have eigenvalues. So what are eigenvalues and eigenvectors exactly? Well, first, to understand these guys, we need to first understand how these linear maps behave. And it turns out that we're going to introduce the first definition, which we will call an invariant subspace. Right? So it turns out, so the whole idea here is that maybe just like with basis, if we can study how linear transformations behave on the basis vectors itself, if we have a vector space, maybe it's composed of the direct sum of a few vector spaces, right? And if we can study how a linear map behaves on, if we have a linear map from V to V, and if we can study how T behaves on each ui for each I, then perhaps we can understand how T itself, T as a whole, behaves. Right? And so it turns out that the issue here, however, is that when we restrict T to UK, right, it might not be that T restricted to UI would have, indeed, that would have a domain of UI, but the range itself might not be UI, right? Range of T restricted to UI might not be UI. So it's not really too useful, right? So it turns out that this is not useful if that happens. But we do have a way to bring the notion of so we first want to introduce the idea of subspaces, that actually we want the range of T actually to be UI, right? And how do we do this? So we want some kind of subspaces, right, that do actually have such a range. And what are these subspaces called? These are called invariant subspaces. So intuitively, what are these guys, right? Let's say, let V be a vector space, and let U be a subspace of V. Right, so I'm going to use this to denote subspace, the less than or equals to for this, right? So if T is an operator, right? So an operator, again, just means a linear map, which where the domain and the codomain are the same vector space. Then U is invariant under T if for all U in U, T of U is inside U. So you could one way you could think about it is that if we can think of it as closed by mapping under T. Right? So in the sense that the image of T, okay, sorry, not image of T. So the image of U under T is just U. So this notation here just means T if this is a set, U is in U, right? And just means that this whole image is U, right? And so these guys are, so it turns out, so from here, what we could look at is that if all of these UIs here, right, if all of these guys here are in fact invariant, so each one of this is invariant under T, right? Then if these guys are each invariant under T, then it's quite easy to study how the behavior of T is. So now, we can look at some very simple examples of invariant subspaces, right? So again, letting T be a linear operator, right? So obviously, the trivial subspace, right? Trivial subspace is always invariant under any linear transformation, right? Because T0 is 0. So obviously, this guy is invariant under T. What else is invariant under T? Well, obviously, whole spaces, right? Because T maps V to V. So that's so also these guys are invariant. So these are always invariant, right? 3. So the whole space is invariant. These are the most trivial examples, right? Another example that's trivial is the null space or the kernel of T, right? And why is this so? Well, we'll leave that to the reader to check. And the last one that is also always invariant is again the whole space, the range, or the image of T. Sorry, not the whole space, but rather the all of the what it images to it, right? So why is this true? Again, this is trivial because it turns out that this guy here, this is just defined as this whole space, right? So, but what is a range T? Again, recall that T is V to V. So hopefully that doesn't confuse you too much, right? The big question is, besides these guys, right? If you have, let's say you're given a linear operator, do we have other invariant subspaces, right? Do we always have invariant subspaces other than those 4? Right? If given an operator. Given an operator. So it turns out that this is true if you have finite dimensional, right? And V, so dimension of V is greater than 1, right? If V is over C, right? For if it's over R, it has to be 2, right? It's kind of interesting to note because C has, so why is this greater than 2 here? Because C kind of have dimension 2 over R. Right, this is unrigorously speaking, obviously. And so this we will prove in a bit. In fact, we'll actually prove it on either within this chapter itself or the next. I'll prove it within this subsection. Okay, so now, but first of all, we want to take a look at very simple, non-trivial invariant subspaces, right? So the idea of these guys here, right, is that, so this is trivial, right? This is also kind of trivial in a way, like, because it's obvious, right? These two here, right? So we don't know if these are non-trivial, right? Because if T was invertible, right, then since V is a finite dimensional space, right, the kernel or the null space of T would be trivial, and the range T would also be the whole space itself, right? So if T was invertible, right, this is not very useful because it is trivial, right? So we want non-trivial examples, right? So first of all, right, we can construct a nice and simple. So first of all, let's take an example of a non-trivial subspace. So first of all, we can take, so let V be any vector in V, right? And let V not be 0, of course, right? Then we can maybe think of the span of V, right? Which is just all the scalar multiples of V. And it turns out that if we so if span of V is invariant under T, right? That means for each vector u in the span of V, right? T of u is also in the span of V. But what does this mean, right? So this means that Tu for all u in span of V, Tu, there exists a scalar, lambda, such that Tu equals to lambda u, right? So if this is invariant, right? If span of V is invariant under T, right? That means that for each u in the span of V, right, then Tu equals to lambda of u. And why is this true? Again, because this is the definition, right? So we called it a span. Span of V is equals to all possible scalar multiples of V, right? So this guy here is called the eigenvalue. This is an eigenvalue of T, right? So what is, and this guy here is an eigenvector, T, right? So if span V, if V was a vector, is such that span of V is invariant under T, then you have eigenvalues of T and you have eigenvectors of T, right? So that's the whole definition of eigenvalue, right? So now we can kind of give the kind of whole formal definition, right? If T is an operator, then so eigenvalues, eigenvectors, obviously these guys are tied to each other. So we can kind of define both at one go, right? And there exists a V in V such that exists a V in V and a lambda in F. So we also require that V is non-zero. Why is this so? We'll see that later. Such that TV equals to lambda V, then V is an eigenvector of T. So why is it and? Because it's not unique. Lambda is an eigenvalue of T, right? So recall the eigenvectors are vectors where if you apply a linear operator to them, it is simply a scalar multiple of the original vector, right? And eigenvalues are what you scale eigenvectors by. So why are we requiring this to not be zero, right? Because it turns out that T0 equals to lambda 0 for all lambda f, right? So we don't want every single field element to be an eigenvalue, because that's, again, not very interesting, right? So, and what this is saying here, right, is that an observation we can make here, right, is that there exists a subspace of V where dimension of U is 1, T has an eigenvalue. This is the observation we can make, right? So we have an invariant subspace of T, U, which with dimension 1, if and only if T has an eigenvalue. And what is this subspace? In fact, it is the span of these guys, right? Yeah? Yes. Okay, so first of all, we're going to let me quickly pull up the textbook itself, right? So the exact definition here, right, is a subspace is invariant under T if you apply T for each U and U, right? If you apply T to U, then T of U also lies inside U, right? So again, so specifically what's happening here? Let's say, so what we're doing is, let's say we imagine this as our space U, right? This is a vector U, right? That we imagine applying T to U, right? That this guy lands here on T of U, right? So if this is true, right, for all U in U, right, applying T keeps U inside U, then U is invariant. Yes, we're not changing the subspace itself. We're just saying that if we have elements of the subspace, let's say this is U2, right? If we apply T to it and it stays inside U, right? So here's, for example, right? Let's give an easy example of something let's give an easy example of something that is an invariant subspace, right? So let's imagine the linear map, right? From R2 to R2 given by so we're just gonna rotate each vector by 90 degrees. Okay, so what does this do? It means, let's say we had a vector here, right? This guy would just be let's say we had a vector, this guy here would be sent to this guy, right? This guy here, if we had this guy, it would send to this guy, right? So let's give an example. So an example of a subspace of R2, right, is a line through the origin. So this line here is simply x is R, right, which is a subspace of R2, right? So this line here. So if we rotate this line, right, if we rotate this line by 90 degrees, right, this guy here is not invariant, right? Why is that so? So t here, this rotation here is a linear operator, right? But if we take this guy here, right, and we rotate it by 90 degrees, right, that doesn't line the line anymore. So that won't be invariant. Does that make sense? But on the contrary, right, so on contrary, let's see why the trivial subspace of 0 is invariant, right? So you apply T to this line here, right? You rotate the 0 vector. So if you rotate the 0 vector here, right, by 90 degrees, it still stays at a 0 vector, right? So in fact, this here, 0, this element here where you apply T to it stays in here. So it's going to be invariant, right? Does it make more sense? Yeah. Sure, yeah. So if you want to shift, so a linear operator we could apply, right? So if we have vectors in R2, we're just going to denote x, y, right? If we want to apply T, we define a T on x, y by, say, shift x by 2. Right, so this is a linear operator. Actually, is it a linear operator? Wait, one sec. No, that's not a linear operator anymore. Sorry. We can scale. We can scale this guy here. Yeah, so if we define a scaling linear operator, right, this guy here, right? And it turns out that this guy here also, so what stays invariant under this, right? If we take this line, right, every point here gets mapped to twice, right? But we keep the coordinate the same, right? Is that going to be invariant? Well, no, because this line here, this subspace here of R2, right? If we take this point here, let's say this point is at 1, 1, right? It gets sent to 2, 1. Right? That doesn't say invariant. It goes here, right? So it already lies outside the line, right? So transforming this entire line, right, doesn't keep it as a line. So this line here is not an invariant subspace of that, right? And actually, if we know that all the subspaces of R2, right? We know all the subspaces of R2, right? They're the two ones, the whole space itself, the trivial one, and basically any line through the origin would be a subspace of R2. So it turns out that since this T here, doesn't have non-trivial invariant subspaces. Yep. No, that would not be linear anymore. So that's the reason why I erased x plus 2 at first, right? Because if you have two different vectors and we add them together, right, that's already not linear, right? Because what do you get? This is at 4. This is not okay. So that's not going to be linear. So that's not a linear transformation, so we don't care about it. You learn about linear transformations in the previous chapter. Sorry, the chapter 3. We are not interested in non-linear transformations. So linear algebra itself is about the study of linear transformations. We don't care if the transformation is a linear, right? Because it literally doesn't matter. All right, it's completely useless. Yeah. Yeah. Translation isn't linear. Yeah, I made a mistake. I love how Paul is deafened right now. Being deafened doesn't actually help because you're not actually learning anything. I guess you can look at the thing, but... Oh, yeah, I guess that makes sense. Yeah, that makes sense. I guess you could... there's no way to unmute yourself, but whatever. Yeah, I guess the stream has better quality. Anyway, so what's happening here? Yeah, they're watching the stream. So we now can move on to... So we now can prove some equivalent conditions to having an eigenvalue, right? So we want an easy way to check whether T has an eigenvalue. Checking if T has an eigenvalue. Well, what we could do is, so the idea is there's a set of equivalent conditions, right? So T has an eigenvalue. So obviously, first of all, let V be finite dimensional. Right? Let T be a linear operator. So lambda is an eigenvalue of T if and only if T is not invertible. Oh, sorry, not T is not invertible. If and only if T minus lambda. So we're gonna, okay, if and only if T minus lambda I is not invertible. And what is I here? So I here is the identity map. Right? And why and so this here can be combined. You can combine this here, right? This statement here, not invertible, with the theorem 3.65, right? So this theorem, what does this theorem state again? T is invertible. So over V is finite dim. T is invertible if and only if T is injective. If and only if T is surjective. Right? So over a finite dimensional vector space. This is only true over finite dimensional vector spaces, these equivalences. We'll talk more about eigenvalues of infinite dimensional vector spaces later. But they are not as interesting, basically. So first of all, let's so all we have to do, so we're gonna prove this. Suppose lambda is an eigenvalue of T, right? So we're actually going to use the equivalent condition that it's injective and surjective, right? So we want to show that T minus lambda I is not injective, right? Since lambda is eigenvalue of T, right? There exists a V in V such that TV equals to lambda of V, right? So what does that mean? First of all, we would like to see how this linear map here acts on V, right? So if this guy was in fact So this means, this means that v is not 0. Right? So if this guy was, so since this guy is here, right? The fact that it's injective, right? What does injective mean? 1 to 1, right? So this means that, again, the only thing that maps to 0, right? So if this was in fact injective, right? If t minus lambda I was injective, right? That means t minus lambda I, the only thing that maps to 0 would be 0, right? So rather, the null space of this guy would have to be trivial. But however, what does the fact that lambda is the eigenvalue of t tell us? It tells us that there exists a non-zero vector, right, of v such that these guys are true. So all you have to do is notice that tv minus lambda v is 0. And why do we use lambda I here, right? So we can rewrite this transformation here as lambda I of v, right? And we applied this as a transformation on v is 0 and v is non-zero. So the kernel of this guy here is not trivial, right? Yeah, I can see Paul's watching on YouTube. I don't look at YouTube comments as much. So like if you have a question, make sure to just open your mic and ask and shit. Anyway, so this guy here is, so this means the kernel is non-trivial. And what does this imply? This implies that t minus lambda I is not injective. Okay. So that's nice and simple. Conversely, right, suppose that t minus lambda I was not injective. Right, so since this guy is not injective, right, that means the kernel of this operator here is non-trivial, right? So let v be in the kernel, right? Then that means that t minus lambda I of v equals to 0. Again, that's simple. So this implies that tv equals to lambda v, right? So again, so lambda is eigenvalue. So this implies that lambda is eigenvalue, right? And again, we can combine, so again, combining this with these theorems here, right? After combining these with these theorems here, we arrive at the equivalent conditions, which I'll show you right now in the textbook. Right, so these 4 of them, right, that is combined with 3.65 there to get everything we want. And again, so now we have given our definition of eigenvalues and eigenvectors. Cool. So we now want to look at some more interesting propositions, right? It turns out that there are some other interesting properties of eigenvectors, right? So if we have let's say we have a list B eigenvectors, right? That turns out that this guy here then is linearly independent, right? So now let's go through the proof of why this is true, because this is somewhat important, right? So this property is kind of interesting, right? This tells us that eigenvectors of a linear operator would all have to be linearly independent, right? So let's prove this. Suppose for contradiction that there exists a list of eigenvectors of T not linearly independent. Right? So we now assume that V1 through Vk is not linearly independent. All right, and also assume that this is the shortest list. So why can we assume that this is the shortest list? right? Because it turns out that if we have a longer, so why are we allowed to assume that the list, so if we have a list of eigenvectors of t that are not linearly independent, right? And it isn't the short, so why are we allowed to assume that this list is shortest? Because if we didn't have a shortest list, right? Then turns out that we can basically just, if we have a longer list, right? It turns out that we can basically just kick out things. We can basically kick out a bunch of still linearly independent vectors, right? And then we'll still be left with a list that will be linearly dependent. So we want to work with the shortest list to make our life easy. And again, all of these guys are distinct, right? So let lambda I be such that t vi equals to lambda I. So all of these lambda i's are some eigenvalues of t. Again, we need them to be these can be assumed to be distinct. All right. So, what this means? There exists vectors. Sorry, there exists more scalars, such that such that the sum here. Okay, I guess dot of is too used to singular. A1 V1 plus dot 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 plus A K VK equals to 0. And importantly, none of these guys are 0. None are 0. Why is this? In fact, none of them are 0. Because this is the shortest list, right? Shortest list, so this means that none of these scalars have to be 0. Sorry, none of these scalars can be 0. Right? So, and why do these exist? This is because we are supposing linear dependence. Right? So, again, since each of these guys here, lambda i's, right? Lambda i's are all eigenvalues. So what can we do here, right? We quickly notice that for each, so we can apply this, right? We can apply this operator. So apply this operator, yeah? So, yes. So it turns out that none of these a's are 0 because this list is the shortest, which I've pointed out just now. Yeah. Let me finish the proof first, then you can ask questions, okay? Okay. So if we apply this operator, right? So t minus lambda ki of these here. So if we apply this on a1 v1 plus dot 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 plus a k vk, right? The right side is 0, right? And so we can kind of distribute the operator in, right? So what do we have here, in fact? It turns out that if we apply this operator here, right, we are basically saying t a1 v1 plus dot 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 plus a k vk minus lambda k, just multiplying all of these. Right? Because I, again, is the identity operator. So think of this as first apply the transformation on them, then subtract off the multiplying by lambda of k, right? And since t, so recall that since each v of these, each vi has eigenvectors, right? Is associated vi. Right? So what this means is that each of this here on the left side, t of vi, that means t of vi equals to lambda I vi. Right? So on the left side here, what do we have here? On the left side here, right? And then here, over here, we have, again, we just have a I v I. Right? And here, this is 0. Right? So, again, recall that each of these, so since none of these are 0, right? Again, 0. And because So since these guys are distinct, right? Distinct eigenvalues. Right? So lambda I is not lambda j for if I is not equals to j. So it turns out that we combine the sum here, right, into the following. Lambda I minus lambda k vi, right? So this here is all 0, right? And of course, again, recall that lambda I minus lambda k is not 0 if I is not k, right? So we rewrite this. So again, expanding the sigma notation here. And then we have a k minus 1, lambda 1 minus lambda k minus 1 minus lambda k plus a k, lambda k minus lambda k of vk, right? But this last guy here, this is 0, right? So we kind of just ignore it, cancel that off, right? So what the contradiction do we derive here, right? This here, right? This is linearly dependent, right? So this list here, well, what is linearly dependent here? In fact, it's v1 through vk minus 1 is linearly dependent, right? But what's the contradiction, right? This is length k minus 1, right? But we said that our list, right, is the shortest, right? So k, that means the list is length k, right? So the contradiction here is that we found a shorter list, right? But we said that, but the problem is that we said the k is the shortest. The length of k minus 1. But we said k is the shortest. Right? And that actually completes the whole proof. So I kind of haven't justified why we can just say that why this proof is working and why exactly none of these are 0, right? And that's probably slightly confusing, right? So there's a lot of assumptions here that you might have issues with. And in fact, let's justify why these assumptions are fine. The first assumption made here is that these guys are distinct, right? Why are so of course it's not very interesting if you have the same vector, right? Like a bunch of times that is linearly dependent, right? Because obviously that's linearly dependent. So we want distinct vectors, right? Secondly, why can we assume the shortest list just now? Because if it isn't, so why can we take a shortest list, right? Because we can just, again, we can throw out vectors, right? You can throw out vectors and still keep it linearly dependent, right? So we're very interested in shortest list. This is kind of like a weird one to wrap your head around. So the first time I saw like proofs that involve the idea of shortest, it was very confusing. But so this one is kind of weird, right? But basically the whole idea here of this being the shortest list, right? Why are we taking the shortest list, right? Where we say there exists such a list, right? We want to take the shortest list, right? Because if we don't take the shortest list, right, we don't really have anything to work with, right? Because we don't really have anything to work with. Or rather, no, we can't take not necessarily the shortest list, right? So if we don't take the shortest list, right, what we have to do so we just have to expand the proof a bit more, right? So we have to add in steps where we just where we throw out vectors until it is the shortest. So we just have to add a step here, right? So this assumption is technically just to shorten proof, right? And in fact, it's kind of a big assumption to make. So if you don't want to make this assumption, all you have to do in the proof is to add in a bunch of steps where basically you keep throwing out vectors from the list until you arrive at a list where if you throw out another vector, it will become linearly independent. So you want so again, you can still get to the shortest without this assumption, right? Why are these eigenvalues distinct? So it turns out that if these eigenvalues are not distinct, right? Let's say we had v1 and v2, but we had the same lambda, right? For those of these. So we're saying that t of v1 equals to lambda 1 of, right? T of v2 is lambda 2 of v2, right? Then that's not good. Because what it turns out here, right, is that we're telling us, right? So if these guys weren't in fact distinct, right, then here, these are in fact going to be, unfortunately, one sec, let me have a sip of water. Ah, shit. So if these guys weren't in fact distinct, right, then what does it break in the proof below here, right? It doesn't actually break too much. Again, so why doesn't it break too much? We just throw out more vectors, right? So if these guys weren't in fact distinct, right, again here, right, more of these guys would be 0 here. Right? So again, it's kind of, again, assumption here. So this assumption, again, just simplifies the proof. Right? If you don't assume they're distinct, right, all you have to do is to throw out more vectors here, right? And so you have to expand the proof a bit more to throw out more vectors, right? And so assuming these guys are distinct, again, not necessary assumption, but makes the proof simpler. What about these guys? None of these guys are 0. Right? So the fact that we can assume none of these guys are 0, again, it's a proof simplification. Simplify proof. Right? If we don't know, again, if we don't know that none of these are 0, right, we will take more steps here. Right? So some of these, again, some of these vectors here will be 0. Right? So we throw out more vectors. We throw out some of these vectors here that are 0. Right? But in fact, we couldn't have throw out all the vectors, right? So you might argue that, again, if we don't add these assumptions in, right? If we don't add these assumptions in, there still isn't a case where you end up throwing out all the vectors and then the list you're left with is of length 0, right? It will always have at least length. In fact, you will always have at least length of 2, right? Why is that true? We'll leave that for the reader to figure out themselves, because that's not too bad. So yeah, that's basically the whole proof. So again, I'll just highlight what the weird assumptions are, right? So why are these assumptions necessary? These are just, again, proof simplification assumptions, right? We don't need them to do the proof, but they just make our life easy. Yeah? So that's great, right? So from this result here, right? This is a kind of somewhat important result. So from this result, what do we get here, right? We get that if t, right, if dim v equals to n, right, then t cannot have the number of eigenvectors. So number of eigenvectors of t, which is the operator again, cannot be more than n. So it's at least, at most, n. So why is that true again? Because linearly independent list, because linearly independent at most n. Right? So this is a simple corollary. Right? So this is actually kind of a powerful result, right? What does this tell us, right? If you have, since we are for eigenvectors and eigenvalues, we are working with finite dimensional vector spaces, right? If we know the dimension, since we know the dimension of space, right? We have an operator, right? We know at most t has n eigenvectors and eigenvalues, right? And this is basically the big concluding. This is actually a very important result from this here. All right. So now we move on to so what time is it? It's 3:45. Okay. So now we'll give everyone a short break for about so we'll have everyone take a short break. So in fact, let's take a break for about 10 minutes. I'm gonna take a rest break for my voice as well. If you have any questions, please post them in chat or ask it. we'll respond to it as soon as possible. Just ignore the fact that it says prompt session on the screen. Okay. Okay, we are back from the break. So I'm just gonna go ahead and move over to the iPad again. Okay, so welcome back. So we're gonna move on to the next part of this. We're gonna move on to the next part of this subsection. Right. So what we're gonna do, we're gonna do polynomials on linear operators. Right. And so why is this topic interesting? Right. And why are linear why are linear operators our main focus here? Right. So here's the whole idea. Right. It turns out that if we have linear operators from a space to itself, right, then the composition, right, T composed of T, right, is well defined. And in fact, it turns out that if we compose T with itself any number of times, it's also well defined. Right? And so this is why we have a bigger theory surrounding the whole idea of linear operators. Right? Again, linear operators, what they are maps from the space to itself. right? And so this is why there's like a whole bigger theory surrounding the idea of linear operators rather than just linear transformations in general. So what first we are going to define what this notation means, right? T to the power of n is just t dot 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 t n times, right? If n is bigger than 0. If n is equals to 0, then t to the 0, right? T to the n is just the identity operator. So we're defining t to the 0 equals to 1. Equals to identity 1. Or some text. So if you want to, this is a helpful way to denote it, right? The identity operator can be thought of as like this fancy 1 here, right? And so this kind of behaves. We want to also define it. We want to define it with the usual rules of our multiplication exponents as well, right? Raising t to n plus m is the same as doing t first and n times, which is just t n times, and then applying t. Again, this applies m times, right? And this is and again, if we have t and m, right? This is the same. This is the same as if we raise it like this, right? And this is easy to check. This is easily proven with proof these in deduction, which will leave as an easy exercise to the reader. Also, if t is invertible, or we can define t inverse to be the inverse. So if t is invertible, right, we can say define t to the negative n to just be t to the 1 raised n times. Right, so this is only if t is invertible. This is only if t is invertible. So now what we can talk about, right, is now we can apply polynomials. Right, and here we're going to basically do what's called abusive notation. Right, so again, let t be a linear operator. Let p be a polynomial. So in this book, I believe the symbol for polynomial is f, p of f. Right, so if p, where p is right, so this is the polynomial, and we define, again, this is a definition, define p of t to be equals to right, and so this is kind of abusive, right, because p itself was defined as p is a function from f to f, right, but for this we just define, again, this is a definition to make our life easy, right? We're applying a polynomial to operator t as this equation here, right? So again, what is going on here exactly? This is t to the 0, right? Just like how this is a to the 0, z to the 0, right? So, and in summary, right, we're basically doing ai t of I, where I ranges from 0 to n. So this is an operator, right? So p of t itself is an operator, which you can apply on vectors, right? And so we now want to see an interesting example of such a differentiation operator. So this is example 5.15 on page 138, right? So let D be the differentiation operator. Okay, so like, what does this mean? It means that if we have for a polynomial, right, we define as the differentiation, right? So consider the polynomial consider this polynomial here, right? So if we define the differentiation operator, so if we apply p to the differentiation operator, what do we have here? We have 7 times the identity minus 3 times the differentiation operator plus 5 differentiation operators squared, right? So if we apply the differentiation, so if we apply this itself is an operator. Again, this itself, we apply the operator to Q, right? If we apply the operator to Q, right, for Q is an element of our polynomials, right? So if we apply P to D, and we take this resultant operator applied to Q, then this is what we get from it, right? And so again, what is D squared? D squared is just differentiating twice. And an interesting thing to note, and why did we define all this polynomial crap, right? It seems not very useful. Well, it turns out that if we have, so let T again be an operator, fixed, right? Then if we define a function, right, where it takes a polynomial, where the space itself, right, and we take this space here to the space of all linear maps on V, right? The function defined by P going to P of T, this itself, this is a linear map, right? And so applying a polynomial on a operator is a linear map, which is very interesting, right? And of course, if we have polynomials of a linear map, right? So if we have P and Q, P, actually, wait, hold on, what the hell? No, this is trivial. We won't even bother. We won't even bother talking about this, right? So it turns out that the properties, right? So if we have two different polynomials, right, and we have a linear map, T, sorry, a linear operator T, right? Then it turns out that multiplication works fine as they do, right? So if we recall that if we have polynomials. So dot is multiplication. If we have polynomials P times Q, right, then this resultant function is just given a P of Z, Q of Z, right? And recall that these guys commute, right? And it turns out that these two properties hold for if instead of Z is replaced with an operator T. Right, and so what this means is that P times Q of T, right, is equals to P of T times Q of T, right? Multiplication in the traditional sense. And again, P times Q. So, and the second statement, P of T, Q of T, would be equals to Q of T, P of T, right? And the proof is kind of easy, so we just see 5.17. Right, this is again, this proof is not very insightful. It's mostly just algebra, right? And it's not very insightful, so we don't bother doing it. So this means that basically what we can do is that if we apply polynomials on linear operators, we can basically just treat them the same as if we're just doing polynomials on, you know, regular ass field elements, right? So, and now what we take, now we ask the question, right? If since T, right? So we call it T. If we have a linear operator, again, linear operator T to D, right? The null space of T and the range itself of T, right? Oh, also, if you don't like it, we can use kernel and image, right? The null space of T and the range of T, these two spaces are always invariant under T. So what about the polynomials, right? If we have a polynomial of T, right? What about invariant subspaces of this operator? This guy, right? So the question is, if we know the invariant subspace of T, is it true that we know the invariant subspaces of P of T, right? It turns out that for the null space, and if we have the range of P of T, these guys are invariant under T, right? So if we take a polynomial and apply it to T, right, then the null space of the polynomial and the range of the polynomial are invariant under T itself. So this kind of gives us a way to search for null spaces and this gives us a way to search for eigenvalues and eigenvectors of T in a way, right? And we'll go through this proof. So why is this so, right? So first of all, let U be in the element of the null space of P of T, right? This means that polynomial of T applied to U is 0, right? So what does this mean, right? P of T itself, right, is an operator, right? If we apply T, so again, this is an operator, remember? So we can compose it with another operator, right? Take T of U, right? And this is basically saying P of T. And this apparently can be done like this. Right? So we apply this here first, right? And then this would be, the inside is 0. Right? So what does this mean? It means that TU is an element of P, null P of T. Right? So, yeah? What's... No, sorry. T is a operator, right? T is an operator, and P is a polynomial, right? What do we mean by operator? An operator is a linear map where the domain and the codomain are the same vector space. Does that make sense? This was defined like way at the start of chapter 5. But yeah, just to remind you, operator is linear map with a domain, same domain and codomain, right? Or you can see that T is a linear transformation from V to V, right? Again, so yeah. So again, we're going through right now is that null T. So we want to show that null P of T is invariant. So let's restart the proof. It's not too long anyway, but since we got lost, invariant under T. So the first one we want to show is this, right? The second one is that range. Also invariant, right? So for the first one, right? So how do we show that it's invariant, right? We want to show that first of all, we let U be a vector in the null space of P of T, right? We want to show that T of U also lies in null P of T, right? So how do we do so? Notice that P of T, right? So what we want to first observe, right, is that P of T, again, this operator applied to this is a vector, right? So we apply this operator here to this vector, right? And in fact, what we can do here is we could compute this operator over here, right? We commute this over here, and since this here, this is 0, right? So T of 0 goes 0, right? And so basically, what are we exactly doing here? What are we exactly doing? Why can we compute that? Right? So linear operators here, why can we compute them? Because T, right, if we take a polynomial, so the identity map, the identity polynomial, right, this is a polynomial, right? Right, so what we're saying here is that P of T, I of T, equals to I of T, P of T, U, right? So if you're confused about why this justification is fine, right? What we're really saying is that T equals to I of T, right? So what we're doing is we're applying the identity polynomial to it, okay? So P of T times T of U equals I of T, well, I of T, instead of commute them around, right? And then this would be apply this map first. And this here is 0, so it's 0. Right? So what does this tell us? Right? What has this told us is that T of u is an element of null P of t, right? Because we applied P of t, right? So again, to lessen the confusion, why is this in del t, right? Because on the left side here, right? Again, so let's take a look at this statement here exactly. All right, sorry, it was a little confusing. Right, so here we're gonna highlight this here is an operator, right? Here's an operator as well. Operator, operator, right? And then we commute the operators around. Right? Right, this the last user vector, right? And then P of t, since u was in the null space, right? The last part here was going to be a 0, right? And since I is the identity, right? So on the left side here, what we are saying here is that if we apply, but first of all, note this again. T of u here, this here itself is a vector, right? So we're saying that, so what we're saying here is that if we take P of t and apply to T of u, right? Where the left side here, operator, and this is a vector, right? What do we get out? We get 0, right? So this means, this implies that T of u is in the null space of P of t, right? But what this has shown us is that for all u and u, right? T of u is at the null space of P of t. So for all u in the null space of P of t, right? Because we've taken u as an arbitrary element here, right? T of u is an element of the null space too. So now the polynomial is invariant under T, all right? And this is for any polynomial, right? And so this proves it for the null space. For the range one, for the range of P of t, right? This is basically the same idea, which we won't go through, but it's in the textbook there for you. Right, so this basically concludes chapter 5a. So to summarize, what did we do here? We talked about eigenvalues, eigenvectors, eigenvalues, and the idea of applying polynomials to operators, right? And one important result, right, is that if dim v t v to v, right? Okay, sorry, not this. The important result from this this section here is that if we have a linear operator, then eigenvectors, distinct eigenvectors of linear operator t, then the distinct eigenvectors of t are linearly independent. Right? So this is the important result of this chapter, right? If we have a linear operator, then the distinct eigenvectors of t are linearly independent. Okay, so now we can move on to the minimal polynomial. My computer started crapping out. Thank you. Okay, so what exactly? So we're going to now, first of all, we still haven't answered the big question we started at the start, which is the existence of eigenvalues, right? Do they always exist? Well, it turns out that if we have a finite dim vector space, at least dimension at least of dim 1 over C at least of dim 1, then it must have an eigenvalue. Right? And this is so if you want to look at the book, this is theorem 5.19. Right? And we are going to prove this because again, seems to be an important result, right? So we're only going to prove like the interesting stuff, the trivial ones or the algebra ones. We basically just leave it to the reader to do because it's not interesting. So let's prove this, right? Again, first we want to let T. So first of all, let V. So suppose we have V is a complex vector space. It's a vector space over C, dim V equals n, and n is bigger than 1. Sorry, not n is bigger than 1, n is greater than or equals to 1. Right? Let T be an operator. Right? So, first of all, what we're going to do is we're going to use the result from just now, right? Which is that, what is the result just now? If we have a linear operator, right, then we have distinct eigenvectors of T are linearly independent, right? So consider the following list. Right, where n here is the dimension of V. Right, so this list here, this length is n plus 1, right? So this list here, so if we rewrite this list as is not linearly independent, right? So what does this mean? Since it's not linearly independent, right? There exists coefficients, right? And not all 0, such that we're just going to label them like this. Right? This here would be 0, right? And not all of these coefficients here are 0. Right? So what are we looking at here? Right? If we focus on just the coefficients here, right? A0, T0, right? A1T, A2T, there's A2T plus dot dot dot, right? Plus ANT to the n. This looks very much like a polynomial, right? So define a polynomial. Define a polynomial with these coefficients. Define a polynomial with those coefficients there, right? This is not constant, right? And why is this not constant? Because if it were constant, right, then it means all of these other things here, everything after A0 would be 0, right? But that leaves us with a list of length 1, which, again, that's ridiculous. That could be very well linearly independent in the list, right? Again, so none of these, so at least we cannot have, so this cannot be constant. So we'll go back to this. If you're confused, we'll go back to this in a bit. Right, so I'll put a star here. If you're confused why this doesn't have to be constant, we'll go back to this, right? So what this tells us, right, is that P T of V, right, is equals to 0. Right, so so this polynomial here, right, where did we get this from? This came from, again, the coefficients, right, to make it sure that this list of vectors here, T0V, TV, T2V, so on T and V is not linearly independent, right? And now we invoke the fundamental theorem of algebra to tell us that there exists a lambda, right? So by the fundamental theorem of algebra, there exists a lambda in the complex numbers such that this p of lambda is 0, right? So we quick digression of the fundamental theorem of algebra. Since chapter 4 wasn't required, what does this mean, right? So this means that every non-constant polynomial in the complex numbers has a root, right? So this means that every non-constant polynomial in the complex numbers has a root. The proof is there's multiple proofs. One uses complex analysis. So you won't be able to prove this yet. So again, complex analysis is C34. One uses algebraic topology. We did this in C27. Again, so don't worry about the proof. So TLDR, don't worry about the proof. You can just use it. Every non-constant polynomial in C has a root, right? So by the fundamental theorem of algebra, there is a lambda in C such that P of lambda is 0, right? So this lambda here seems to be our eigenvalue. Right, so what does it mean, right? So what we can do is we can take, since P of lambda equals to 0, right? Right, we can do polynomial division. There exists a new polynomial. There exists a polynomial Q such that P is equals to, so we factorize it basically. So P we can basically factorize out of root. So we factorize the polynomial P, right? And what this tells us, right, is that P of T, so applying the operator again here, is equals to right? And so we're saying that applying the operator P of T to V is equals to this, applying the operator T minus lambda I on Q of T to V. Again, so to avoid confusion, what is exactly going on here, right? If we actually substitute what this P of T is doing here, right, you can think of this as your Z, right? And this is just Z minus lambda. Okay, the I doesn't really do anything. You can think of this as just Z minus lambda. So Z is this guy, and lambda is just this guy, right? So to clean up the notation slightly, right? If we ignore the V for now, P of T is simply just T minus lambda, right? And Q of T, right? Which is exactly what we're batching up. We're just swapping out Z for T. And because we're dealing with linear operators here, we need to add the I. Because we're applying a V, we're adding a V here, right? So don't get too confused here, right? So what is interesting here, right? Degree of Q is going to be less than degree of P. Which is pretty obvious, right? Because you factorize it, so the degree is going to be lower. So this means that Q T of V, it cannot be 0, right? So why is that here? So looking here again, 0 goes to T minus lambda I, Qt of V. Right? So because Q having a smaller degree than P, right? And this is covered in the previous section, right? But it turns out that this if you factorize out lambda, right? Right? So this lambda here, lambda is not a root of Q anymore. Right? So yeah, so this guy here, all this is telling us, right, is that the so basically, okay, sorry. Yeah, we're just basically applying the division algorithm here, right? And because we factorize it over C, right? What we are saying here, right, is that and what why is this so interesting, right? Each of these here, this factorization here is unique, right? So why is lambda not a root of Q? This actually needs to go to 4.13, right? Theorem 4.13. Right? Again, don't worry too much about this. Right? So where were we again? So because lambda, this lambda here is not a root of Q, right? What is going to happen here? This means that t minus lambda I here, right? This is not zero. Right? So this here now we're treating this as a vector. Right? Linear operator. And recall again from 5a, right? We proved the result, right? Where we have eigenvalues, eigenvectors of t. If this equation here, this guy here is non-injective, right? So since this is not zero, right? T, so if we treat this guy here as w, right? Tw equals to lambda w, right? But let w be q t of v. Right? So we found that this here, lambda is, well, what we found here is that lambda is an eigenvalue of t, right? So we are basically done with the proof, right? So again, to summarize what happened with this proof, right? We constructed, this proof is kind of involved. So what we did was we constructed a list here of a bunch of vectors, right? And this list was very specially constructed, right? Because it turns out that what we can do with this list is take it a polynomial, apply the fundamental theorem of algebra on it to obtain a root, and take that root and show that it is in fact a eigenvalue, right? And this is kind of weird, right? This was weird, right? We use because the fundamental theorem of algebra, right, is taking polynomials and complex numbers, right? But we used linear operators, right? We used linear operators in the space of polynomials, right? And it still worked. And that's kind of weird. Why is that? Why did that work? Honestly, I don't know. So yeah, but it's very interesting, right? We applied something that seems to be not very related to linear algebra, right? We're applying polynomials. We're dealing polynomials. And yet when we put in linear operators into there, it works fine. And we use that to find eigenvalues, right? And that's so weird. But basically, we have, I mean, yeah, probably, but yeah, I mean, yeah, I know. Yeah, but like, I guess determinist isn't the most insightful answer to this, because like, it doesn't really tell you much more insight to it, you know? Eh, yeah, but anyway, it's kind of weird, right? So anyway, this proof basically shows that if we have an operator, right, on a finite dimensional complex vector space, and the complex vector space itself has to be non-trivial, right? It must have an eigenvalue. And so this basically is a pretty nice and big result, right? So this result here is important, right? So this we call the existence of eigenvalues, right? So it turns out that our questions have been basically answered. So now, why? So there are some things here, right? It's important to look at counterexamples, right? So why do we need finite dimensional? Right? It turns out that if it's not finite dimensional, we can find operators without eigenvalues, right? So we define a linear operator. So we're going to define a linear operator by saying TP need to do this, right? Define this function, right, by taking P of Z and mapping it to a new function. And what does this do exactly? Right? If P, right, then in terms of the degree of T of P, right, so this transformation here, so basically what this does is it basically raises the degree, right? So exactly, for example, if we have Z, right, Z itself gets mapped to Z squared, right, or like 3 Z plus 5Z5, right, that becomes 3Z squared plus 5Z to the 6, right? So this operator here increases the degree, right? If P is non-zero, the degree P of T, right, is greater than degree of P, right? So there's no way that there cannot ever exist, right, a lambda such that TP is lambda P, right? Because lambda P is equal to degree of P, right? But we said the degree of P is less than degree T of P. So T itself has no eigenvalues, right? So in here we replace the finite dimension with infinite dim, all right? And it immediately did not work, right? So it turns out that, again, the hypothesis of infinite dimensional is very, very important, right? Now, why do we need it to be complex, right? I will let you see. So this here is example 5.20. Why do we need it to be complex? We need see example 5.9, right? For why it needs to be complex, right? Sorry, we are overrunning a bit today, so whatever. So now we have proven this existence of eigenvalues, right? We are going to talk about so we're going to talk about minimal polynomials, right? So this is still kind of so we're going to go a little bit faster here, because, well, we're already running on time. So first of all, monic polynomial, right? Monic polynomial is polynomial with where the coefficient of highest degree term is a 1, right? So for example, let's say we have like 3z squared plus 5z5 plus z to the 9, right? This guy here, this is a monic, right? What's not a monic is if we change this to 2, right? If we add a 2 in here, this won't be a monic, right? So again, the highest degree, so what we can think about it is a monic polynomial is always of the form, it's always going to be the form of a0 plus a1 plus a n minus 1 z n minus 1 plus zn, right? So this is what we call a monic polynomial. And now we can talk about, so theorem 5.22 basically says that if we have a finite dimensional vector space, right, if v finite dim and t is a linear operator, then there exists a unique monic polynomial, right, smallest degree, such that p of t is 0, right? And degree of this polynomial here is less than dimension of v, right? We don't have time to go through this proof, honestly, because like we're kind of running late. So again, just look at the proof yourself. It's 5.22, right? We can't go through this proof. And now we can talk about minimal polynomials, right? And so this is interesting. Minimal polynomials, right? The minimal polynomial of t, right, is the unique monic polynomial, right, of smallest degree, such that p of t is 0, right? So this result here, p of t, tells us, right, that if t, the v is finite dim, right? T is an operator. Then t has a unique minimal polynomial, right? So what does it say is that every linear operator over a finite vector space has a unique monic polynomial. It will always have one. And so, what is the result? What is the idea? What is the interesting result? What's the whole idea of monic minimal polynomials? Honestly, I kind of don't know too much. I'm guessing it's probably for finding eigenvectors. Yeah. I don't really know why we use minimal polynomials right now, but they're kind of interesting in field theory. But anyway, oh shit, yeah, it was just right. It was just right there. 5.27. Yeah. So 5.27 says that the zeros of minimum polynomial are the eigenvalues of t. The zeros of minimal polynomial are eigenvalues of t. Right, so if you have a minimal polynomial of t, you have the eigenvalues of t. Right, if v is complex, these are, by the way, are the eigenvalues of t. These are exactly the eigenvalues of t. Like, there will be no more, right? If you find the minimal polynomial of t, you have the eigenvalues of t, and that's it, right? So if v is complex, then so it turns out so if v is complex, it turns out that if we have a minimal polynomial, right, it splits over c. Oh, okay, so shit, sorry, that's doesn't help, right? Has the form right? So if we have if v is a complex vector space, right? So v has a field over c, right? Then the minimal polynomial has this form, right? You can always decompose it into all the eigenvalues. Note that there may be repetitions, right? So like not all these are unique, not necessarily unique, right? But each of here, what we have here exactly is that lambda 1 to lambda n are the eigenvalues, right? So again, we kind of really can't get through it. Can we go through this proof? Should we go through this proof? Okay, does anyone want to see the proof, or should we not do the proof? Yeah, I kind of want to go through that, but like if we can't, we can like, cause like we've kind of cause it kind of taken out a lot of time. It's already been like 1 hour 40 minutes, so like yeah, so maybe we'll just do that next time. Cause 5A and 5B is so like it's really long. Like I took like an hour plus just to go through 5A. So, um, you know what? Okay, I think we should go through this proof. Um, I don't know. Okay. So, okay here. Okay, so I'm gonna switch my screen. Okay. Oh, sorry, not the break time screen. Wrong screen. So this. Okay, let's go to this. Let's go to this. Right. So here's a here. So we have either. So we can either go through the existence uniqueness degree one. This is kind of okay. I guess it's not as important. Um, is it constructive? Let's see. Um, yeah. Okay, it's not that. Okay. Well. Maybe I'll just like prove this at some other time or something. Whatever. Yeah. This guy here, right? Oh yeah, to compute a minimal polynomial. Yeah. Mm-hmm. Ooh, right. Yeah. Okay, I guess. Yeah, I guess it makes sense. Yeah. Anyway, but yeah, I don't know. These are the existence is kind of like a very theoretical statement, which is nice. So, the computation ones are kind of annoying. Are these proofs? Yeah, I guess. Should we prove that? Does anyone want to see any of these proofs, or do you want to just like call it for today? We can finish. We can go ahead and finish off this here. The we'll go through some more results. Do you want to just like go through a few more of these and then we can stop? Cause like, yeah, I think everyone's dying. So, okay. So we're kind of just gonna quickly go through the theorem statements. The proofs, I think I'll just leave. We'll just leave it to figure out our own time. I might record a short recording going through the proofs, but we'll see. Um, the proofs are going to take very long to go through because, like, yeah, yeah. I mean, all of the proofs I've been going through, like, I have to like expand on the details, of the proof, so it takes kind of long. You know what? I mean, okay, yeah, proofs are not supposed to be short to go through anyway. So, let's go through some of the results first, and then if anyone wants to stick around, like, maybe we'll go through the proofs some other time. Yeah. So because I think the results are pretty important. Like knowing the results are kind of like more important than the proofs, which are like the proofs are like as long as you know the skeleton, you know how to prove it. So let's look at this guy here first, right? So if you have a polynomial, right? That if you apply it onto your operator and it gives zero, right? The polynomial of the operator of the polynomial is zero, right? That this turns out that Q is a polynomial multiple of the minimal polynomial, right? What this is saying here, it's basically, what this is basically saying here is that if you find polynomials that give you a zero operator, that you know it's like some multiple of the minimal polynomial, right? I guess I don't know if that's helpful. Like, it's constructive. Sorry, not constructive. Um, yeah, it's not the most constructive. Well, it's not that constructive. Okay, I guess yeah, yeah, I guess good. Anyway, so a minimal polynomial restriction operator. A minimal polynomial of t is a polynomial multiple of the minimal polynomial of t of u. Cool. Yeah, t is not invertible. If and only if the constant term of the minimal polynomial of t is zero. This is kind of an interesting result, right? We'll just quickly go through because it's short. So if t is not invertible, if and only if zero is an eigenvalue of t. So what this means is that, what is that? What is that eigenvalue? Oh yeah, there is so there is the null. So zero is the eigenvalue of t if and only if it's like a null. It's in the null. It's So there means there has to be a non-zero element in null space, right? Because eigenvalues have to be multiplied to non-zero vectors, right? And it turns out that zero is a zero. Zero is a zero p, right? And obviously, since zero is a zero p, the constant term is zero. Okay, cool. Very trivial. Honestly, these are kind of like just annoying results. Yeah. Yeah, I don't know. I think we'll just skip these. These are just annoying results. Um, yeah. Okay, whatever. We'll just skip those. Those are annoying results. We'll do 5C next time. Cool. All right. Thanks everyone for watching. We're just ending this now. So if you have any questions, post in chat. Yeah, if you have again, if you have any queries, ask in chat. Hopefully that wasn't too confusing. We did spend a long time going through some of the proofs. But yeah, happy New Year's and see you all in the class in like 5-6 days. Yeah, but anyway, so yeah, it's almost no, it's almost over. So the next session is on the 5th. Is it on the 5th? So it's probably gonna be the 5th. If you still have any questions, again, feel free to ask in there. Yeah, let's do it the 5th. So we're hopefully gonna go through 5C, 5D, 5E. And then we want to maybe get to inner product spaces, which are kind of nice. Yeah, the inner product is a bit more theoretical thing. So we want to maybe get through that. But yeah, we actually... Yeah, that's true, yeah. So yeah, but yeah, the eigenvector and eigenvalue thing is like, it's kind of very theoretical. So, well, it's okay. The book presented pretty theoretical. Like, I'm pretty sure they're important, pretty sure they're important. Yeah, I'm pretty sure it's important, but anyway, these are just results. Okay, so hopefully everyone didn't die, but brains did. Maybe your brains did die, but yeah, that's normal. If your brains did die, please ask questions. Again, please ask questions. If the proof is confusing, please ask questions. All right. Yeah, like the proofs kind of confuse everyone anyway. So, and to be honest, I kind of didn't look at this too much beforehand. So, yeah. Okay, have a nice day. Yeah. Oh my god, dude. Dude, I looked at it this morning. I literally looked at it this morning when I woke up. Yeah, like half the proofs I had to like construct on the spot myself, like looking through it. Anyway, that kind of sucks. Yeah. Anyway, so yeah. Mm-hmm.